Welcome to my project Bazaar. We are going to see the product for A65nm cryptographic processor for high-speed pairing computation. Next we are going to see the abstract for our product. The pairing-based cryptography has been applied to provide efficient solutions to several long-standing problems in cryptography, such as three-way key exchanges, identity-based encryptions, identity-based signatures, and non-interactive zero-knowledge proof systems. Cryptographic processes are becoming the standard way to enforce data usage policies. The system presents a flexible and high-performance processor for cryptographic pairings over pairing-friendly curves at high security levels. The proposed pairing processor exploits the parallelism using three independent pipelines which execute basic reducer instruction set computer instruction, FP2 multiplication and FP2 addition subtraction. As cryptographic schemes based on pairings are introduced and investigated, the performance of pairing computations also receives increasing interest. The pairing computation is relatively complex and slow compared with other popular public key primitives such as reversed Schmidt-Adelman or curve cryptography. For pairings over ordinary curves defined over prime fields, the computation can be broken down into module multiplications and additions in the underlying. Due to the suitability for parallel implementation and the low cost for multiplications, residue number systems have been introduced and studied for longer integer modular multiplications with area complexity of O(n). The time complexity is O(1) for a multiplication. Moreover, laser reduction were first deployed for pairing by Scott and then generalized by Addons. Finite field computations including modular multiplication, inversion and addition usually constitute over 90% of the pairing computation in software implementations and is of the highest priority. A multi-cycle Montgomery multiplier and a multi-cycle adder are implemented, but the multiplier is based on the algorithm in which allows using carry-save additions and carrying out multiplication and reduction simultaneously. Next we are going to see the flow diagram for our product. The 16x16-bit multiplier is implemented. To the 16x16-bit multiplier, it is divided into two sections. 4 inputs A, B, C, D, all are 16 bits inputs as given to the input to the 16x16-bit multiplier. The 16x16-bit multiplier consists of VPG unit, hybrid adder circuit and 32-bit output. The two 32-bit outputs are given as input to the modular section. The modular section outputs the data. It is given as input to the 3-to-2 compressor and 32-bit carry look-ahead adder. The 3-to-2 compressor output is given as input to the 32-bit subtractor unit. The 32-bit carry look-ahead adder output is given as input to the transmitted output. The transmitted output is given as to retrieve the public key. Finally, the public key is retrieved. The processor employs a RISC architecture with 5 pipeline stages such as instruction fetch, instruction decode, execution, memory and write back. The modular multiplier and the modular adder subtractor implement the FP square arithmetics. Next we are going to see the output for our product. We use the software Xilinx 14.2. To create a new project, click on File and then New Project. Specify the folder to which you have to save your project. Then click on the project and then New Source. The program space will be created. There you can write your program. First, after writing your program, we have to simulate. For simulation option, click on simulation, cryptographic, and then simulate behavioral model. The simulation process will be executed in the ISIM. Here we have to give the input data. For A, the input data is 16 bits. For B, the input data is 16 bits. To give the values, right click on the bar and then give force constant. Input of the C is also 16 bits. The input of D is also 16 bits. And we have to give the input 32 bits in case of P. There are 4 selection lines and we have to give the selection bits. Then click on the run option. The output will be shown. Then minimize the ISIM. For the implementation, you have to click on the implementation and then implementation design. We can see the synthesis report on this design. Here I have already run this implementation. To rerun, you have to click the rerun purpose. For the RTL diagram, click on the synthesis exists run and then view RTL schematic. Then click on OK. Then click on add and then create schematic. The schematic will be created. Double click for the technological diagram. Thank you.